All right, going back to some thermal equilibrium here. Multiple choice question. So here, looking at substance A and B, initially at different temperatures, come in contact with each other to reach thermal equilibrium. Mass of substance A is twice that of B, so this is what I mentally do to myself in my brain. So A equals to B, and then the specific heat capacity of B is twice the specific heat of A, so B equals to A for specific heat, right? And which statement is true about the final temperature of the two substances once thermal equilibrium is reached? So, okay, what can we say about that in terms of looking at our choices? The final temperature is going to be closer to initial temperature of A, or is the final temperature going to be closer to that of B, or should they be midway? Based off of the data they've given. Yes?
Wouldn't it cancel out?
Well, yes, that's the whole point of the idea that the mass of A is 2B, and the specific heat of B is 2A. So, one is doubled for each one, then they end up, the masses and the specific heats end up canceling out each other. In terms of magnitude, yes, and therefore the temperature should what? Be midway, exactly. So that's the whole point there. Correct. Alright, so this is a really good one. This goes through the whole dissolution process, and it helps us recall some of the stuff that we need to know for our heat problems as well. We have 15 grams of calcium chloride dissolved into 100 milliliters of water at 22.5 degrees Celsius. The final temperature is 32.2. After dissolution took place, consider the water and what happened to the temperature. What happened to the temperature? Increases, right? Temperature increases, goes up. So what does that mean about the average kinetic energy?
Increase.
Should also increase, right? Increases. If you don't remember this, the definition of temperature is equivalent to the average kinetic energy of the particles. So if the temperature is increasing, so is the average kinetic energy of the particles. So what does that tell you about the speed of these particles? Also increases because kinetic energy is equal to the energy of motion, right? So that means they must be moving faster. Okay? Follow me so far?
Yes.
Okay. Now, this is where it gets fun. Was the dissolution reaction endo or exothermic?
Exo, it's releasing heat into their surroundings, which is water.
Correct. It is releasing heat into the surroundings, and I would use the approach as where does the thermometer sit? Surroundings. Like if you were to touch this beaker, it would feel warm to you. You are also part of the surroundings. So remember that the thermometer always measures from the surroundings. So if that goes up, it means heat's being released. So therefore it has to be exothermic. The system is going to be the calcium chloride mixing in the water. So actually those two are involved in the system. The thermometer, though, being in there, still also is not the chemicals involved in the system. So therefore, the thermometer is feeling the warmth as you would feel the warmth if you were observing this dissolution. If you touch the beaker, it would feel warm to you. That means it's being released because we are located in the surroundings. Heat going from the system to the surroundings means it's being released, okay? So do remember that. Thermometer, temperature probe, always is going to be for dissolution and for chemical reactions, that always is from the surroundings perspective. Now, this is the hardest part. Explaining this, and I've seen this question a few times, different in multiple choice and in FRQ representations. So, are the strengths of the interactions between the particles in the solute, okay, the solute's the CaCl2, okay, and between the particles in the solvent, okay, so this is H2O. Before the solute and solvent are combined together, greater than, less than, or equal to the strengths of the interaction between the solute and the solvent particles after. Okay, so this is after. So before versus after. And before here, what are we talking about before? The forces in here, what kind of forces in CaCl2? This is an ionic bond. All right, that's ionic bond. What kind of forces do we have in our water?
H bond, LDS, and active.
Okay, H bond, yes, dipole, LDFs, but you could say predominantly, the predominant IMF is H bonding. And also, by the way, some of you were calling H bonding bonding. It's not bonding. Remember, H bonding is a type of IMF. It is not intra. Intra forces are bonding. Inter forces are IMF. So make sure that you keep that separate. So these two things added together versus what would be the thing between the solute and solvent afterward? What would we call that?
Ionic dipole.
The what?
It's ion dipole.
It is ion dipole. Very good. So this is ion dipole. So this is the after effect. So we have the two before and the one after. Now, you tell me, the CaCl2 coming apart, breaking that ionic bond, is that endo or exo?
Endo.
Endo. Bond breaking is always endo. Very good. Overcoming forces, like predominantly the H bonding, although the other two are in there too. Overcoming forces, is that endo or exo? Endo. Anytime you have to overcome forces or break bonds, you need energy to do that. It must absorb energy. So that process is also endo. Forming a bond between your ion and your water, which is called the ion dipole force. Forming is warming, so therefore that particular piece of the dissolution is exo. So you have two endos and one exo. Now, so it has to be the net of the processes. So these two together over here, these are endos. This one is exo. Now we know overall it's what?
No, overall it's exothermic.
Yes, we know that it's overall exothermic. So which one has to be higher in order for it to release energy?
Yeah, the bonds formed need to be stronger in order for it to be negative. You can also use the equation for bonds broken minus bonds.
And that's what I'm getting at. Exactly right. I went there and used that formula too. So if we know delta H is negative because we know it's exothermic because the temperature increased, so we know that the thermometer is reading it from the surroundings. That means delta H is negative, right? So in order to get delta H to be negative, which part has to be larger and has to have more in it? Well, bonds forming and forces forming. Now remember, the process of forming the forces, which are weaker, that isn't as much as a bond, but the ion dipole forces that were formed, obviously that numerical value was larger because when you subtract it, you get a negative delta H and energy is released overall. Okay, so delta H is negative, the bonds or forces formed must be stronger or at a higher energy than the bonds or forces broken here. That is why after dissolution forces must be stronger than the before dissolution forces. And they love to ask about this because in that process of dissolving, you have a bunch of things going on, right? So use that bonds broken, forces broken, whatever. They don't like to say forces are broken. We like to say forces are overcome if we're using correct terminology. But keep that in mind. I just, like, since we are breaking a bond and we're overcoming forces here, I just kind of put them together as bonds / forces. But it is the same thing. Anytime you overcome any kind of force, whether it's a bond or just an IMF, you need energy to do that. Anytime you form a bond or an IMF or some kind of force, it is going to be exothermic. You're going to release. Forming is warming, axing is taxing. In here, though, we have both things going on, so you have to look for whichever one's going to be the net higher of the two. Or technically the three, because we have two things that are being broken or overcome, and we have one thing that is forming here. Okay? But this is a classic question. They like to ask it about the dissolution process. So make sure, I did this one specifically for that reason, because I see it quite frequently. So I wanted to make sure that you understood this arrangement and the way that you should word it. Question?
So if the reaction was endothermic, the things between the
You mean this
solute-
dissolution process, if the temperature
Yeah.
went down and was endothermic, then you would reverse it, and you would say the forces in the solute and solvent before, or the bonds and the forces in the solvent and solvent before would be greater, yes, it would be the reverse, exactly. Exactly correct. And as a matter of fact, you might see an example like that if you look at some of the practice FRQs I put up. All right? And I do highly recommend, if you don't even have time to do them, but you should go through and like at least read the questions and read the solutions so that you're practicing the terminology, or you're like hearing it again, or maybe read it out loud to yourself so you're hearing it. Because a lot of this isn't necessarily the knowledge, it's can you write the correct terminology down in time, okay? So the only way you get better at it is if you hear it and practice it and write it more and things like that. Okay, so let's off to calorimetry. Dissolution and reactions. Kind of already highlighted this point in the last problem, but if two reactants at the same temperature are mixed, the resulting solution gets warmer. That means it's exothermic. Endothermic, the reaction cools. Okay? And remember that is due to the fact that the thermometer is always considered to be in the surroundings. Remember, it's not actually part of the system. The system is only the chemicals involved in either the dissolution process or the reaction taking place. Okay? So that leads us to this setup. Okay, using QAQ MCAT, okay? For delta H reactions and for delta H solutions, we use this setup. QAQ is the heat released or absorbed by the aqueous solution. And that's where our thermometer is located. So obviously that's going to tell us which way the energy is going. If it warms up, that means energy is released. If it cools down, the energy is absorbed. So in order to find the Q solution or reaction, we have to change the sign on that. Because we know what's reaching the thermometer is opposite of what's taking place in the system. Now, here I should have also wrote in here, this could also be reaction. This is just the additional step of calculating delta H. So this is the last way of being able to calculate delta H. You find the heat of whichever process you're dealing with, and you divide it by the moles of whatever was inputted, basically. Because we know that delta H is kilojoules per mole. It is measured that way, right? It's going to be kilojoules per mole of that thing. Now, in order to calculate that, we have to divide it by the amount that was used in that particular reaction. So this is the fourth way. We have Hess's law, we have heats of formation, we have bond enthalpies or bond energies. This one is the calorimetry data. You use it to figure out the delta H from it. Okay? Now, for example, this is a dissolution process. We're taking some potassium bromide and dissolving it in water. And we end up looking here, the temperature drops from 18 to 17.279. Okay, assuming that all of the heat absorbed in dissolving process comes from the water, and that the specific heat of solution is that of water. So I'm going to go with the 4.184 here, because that is our specific heat of water. We could go look that up, on our table or whatever in the beginning of the notes. Now, is this process endo or exo? This would be endo because the temperature dropped, so we know that. Okay? Now, we need to calculate Q solution for this. So first I'm going to be looking at it from the surroundings perspective because that's the data that it gave me. One other thing I forgot to mention back here, we should probably go put this in. The M part of MCAT here. Okay, the M part of the MCAT is the total mass of the solution. And you'll see these calorimetry problems are worked in solution, either directly done in the water or like in the bomb calorimeter, the little bomb chamber is surrounded by water, so the water absorbs the heat or releases the heat. Okay, so here we have to look at the total mass of the solution. And I reference that because here we are adding 1.34 grams of KBR to it, and we have 74 grams of water. So our total mass of solution should be what?
7534.
Yeah, we have to add those two together. So that would be what we would need to do for the mass part first, is add 74, not 7.4, but okay. 74, so this is, yes, 75.34 grams of water, of mass, okay. Now, and what I would do, you don't have to do this as a separate step, this is what I would do with these problems. I learned this last year from one of my students who like to put things together so that everything moved a little bit faster. So let me show you this. QAQ, MCAT, right? That's what we're using as our formula. So to solve for QAQ, then I would do 1.34 plus 74 times my 4.184. This is grams, right? And then I put in my temperature change, 17.279 minus 18. You write all the calculations in, although you can do them separately, but like you write them all into the formula, then all you have to do is plug, chug, get your answer. And you're showing me that you are adding these together in that process, so you don't have to do it as a separate step. So this helps speed it up a little bit. Okay, you see what I'm talking about? 4.184 is the specific heat of water. It's on the table beforehand, but in the notes, but specific heats will be given to you. Don't worry about that. You won't be expected to memorize specific heats. And I don't think that one's on the formula sheet, but it might be. I will check it. Here, let me look. See if it's on here. Specific heat. Nope. They usually give you the specific heats in the problem, so I will do so as well. Okay, what do we get for QAQ? Isn't it like 227 or something?
Yes, negative 227.
Negative 227 joules, right? Okay, so that's QAQ. So all we have to do to find Q solution is do what? So Q solution is now changing the sign, so this is positive 227 joules. You don't have to put the plus, I do because I like to make sure that I'm keeping my sign straight, my direction straight. Now, the next step here, we need to figure out delta H. And how do we measure delta H again? Or how do we calculate it? Q over what? Q over mole. And that will give us the heat per mole by doing that. And here we know how much of our solvent is being dissolved, so we can easily do what there? Divided by the molar mass to find the moles. So we do that. Pretty sure it's 119 from last class, but somebody can check that. Yes, 0.0113 moles KBR. All right. then all we have to do is do Q divided by moles here. Now, what I would suggest you do as well beforehand, because delta H is expressed in what unit, usually? Delta H is usually kilojoules per mole of the substance here, or per mole reaction, depending on if we're talking about a chemical reaction. So, here, since we're going to change it to kilojoules, I would go ahead and just move this over, like divide this by 1,000. Move that over 1, 2, 3, right, to start off with. So this now changes to kilojoules. So we do 0.227 kilojoules divided by our 0.0113 moles. And then we result in our delta H in kilojoules per mole, which looks like it is going to be positive 20.1 kilojoules per mole. That's per mole of the KBr being dissolved. And delta H is positive, which should correspond to our temperature decreasing, because both indicate endothermic, right? So you should make sure that your sign matches the way the temperature went. That's the best way to know which sign you have. Yes?
Would we use points if you just left the answer in joules per mole?
Yes, typically they'll tell you, but you should report delta H in kilojoules per mole.
Alright.
Now, usually they'll tell you to report it in that. Okay? So, yeah. All right, now, this one is a heat of reaction. We have silver nitrate reacting with hydrochloric acid, getting silver chloride and nitric acid out of it. A little bit different take here, okay? We have 50 milliliters of 0.1 molar silver nitrate. We have 50 milliliters of 0.1 HCl, and we end up, the temperature goes from 22.3 to 23.11. So what does that tell us right here? Yes, this is XO, so we should expect our delta H to be what? Negative delta H. That's what we should expect. Okay? Now, the other key thing about this, for these problems, what you should notice too, looking at our reaction, what is the mole ratio of our reaction?
1 to 1.
1 to 1 to 1, which is nice. Now, also looking at our two reactants, we have 50 milliliters of 0.1 for both. What does that also tell us?
There's going to be no.
Same molarity, same volume, so that means same moles are being contributed to the reaction, right? So, in this case, this is not a limiting reactant problem, because you have the same input of each one is the same moles. You have the same mole ratio, so neither one of them is going to run out. They're going to run out together at the same. Okay? So you don't have to treat this one like a limiting reactant problem, because everything is the same moles. But if you did have one where the mole ratio is 1 to 2, or you were starting out with different amounts of your reactants, then you have a limiting reactant problem. Then you have to work it to whichever one is going to run out first, and that's the one you would use for the mole part on the bottom. Do you understand what I'm talking about?
Which is limited reaction.
If you were given different amounts though, where one of them is limiting and one of them is excess, you would want to do it out of the one that's limiting. Okay? Now, here, same idea, except for delta H for this reaction, assuming the combined solution has a mass of 100 grams. Well, that's nice. They told us the grams. So this is our mass up front. The specific heat, as you can see, is listed here. Now, another thing. Sometimes they'll give you volumes of the solution, and they don't tell you the grams. But, like, put in parentheses next to it the density. So what should you be able to find if you have the volume and the density? You should be able to find the grams. So if they give you the density, and they do this sometimes in that problem set where they give you the density, they expect you to find the mass from that, okay? And if you don't already know, density of water, which is the majority of these solutions, because the majority of these solutions is water, the density is 1 gram per milliliter. So that's usually pretty easy. And as you can see, 50 milliliters, 1 gram per milliliter, that's where that 100 grams comes from. Just something to point out. You'll see one like that later too. So all we have to do now then is find QAQ. Here's our MCAT. Put in the 100 grams. 100 grams. Specific heat, 4.18. And the temperature change, 23.11 minus 22.30, right? And we get QAQ. What do we get for this number? Is it 339? I think it's 339. Somebody calculate it? No.
Yeah, it's 339.
Okay, so this is 339 joules. That means Q solution is going to be negative 339 joules. And then what should we do from that point? Change it over, right? Over, and this is going to be 1, 2, 3, so 0.339 kilojoules. Don't forget the negative sign. That helps very nicely. So we've already got this ready to go to put in to get us to delta H. So we found Q solution. Now to go to delta H, what other little piece do we need? We need moles. So it doesn't matter which one we use, because guess what? They're the same. And now we have to remember our what? Molarity equation. Or you can use dimensional analysis, which I like to do. You could do it this way: 1 liter equals 0.100 moles, right? You could use the molarity equation, or you can go that route to find your moles. 0.005. And then all we have to do to find delta H, remember delta H is going to be Q over moles. So we divide these two, what do we get? What do we get?
So you're dividing.
We're dividing the 0.339 by the moles. And we end up with negative 67.8 kilojoules per mole. Although, I guess you don't have to write it like that. That looks weird. Mole. So, this is for every mole reacted, you're going to produce negative 67.8, or release that amount of energy to the surroundings. Yes?
So, if the mole ratio is like different, would you do the beginning part like the same and then just divide it by moles of the limiting reactant?
Correct. If there was a limiting reactant here because the mole ratio is like 1 to 2, or they gave us different amounts, I'd have to figure out which one's limiting first, yeah, before I begin. And looking here, I suppose, I would probably just, what did we go? We went with 3 there? Why did we go with 3 there? Oh, I think we go with 3 at the end. Like, this probably should have been 4, but that's okay. Or it could have been 2, because this has, when you subtract that, that's going to give you 2. So when in doubt, go with 3. Let's go with 3. I think my answer's in 2, but I would still go with, I like this one. This one's better. Kilojoules per mole. Alright. Bomb calorimetry. Reactions can be carried out in a sealed bomb chamber such as this one. So the little bomb chamber in here is surrounded by water. And they stick a thermometer in the water, and then they have like some way of like sparking it to get it to go kaboom in there in the little bomb chamber. And then they can, and this is highly insulated so that they can measure the temperature change in the water, okay? Like so. The heat absorbed by the water is very good approximation of the enthalpy change for the reaction. And there's a basic formula if they give you the heat capacity of the bomb calorimeter to begin with. Alright, so if they give it to you, then you can just use this formula, which is nice. Bomb calorimetry heat capacity times the change in temperature gives you the heat evolved in that reaction, whether it's absorbed or released. Most of the time, hence bomb calorimetry, these are going to be exothermic. All right. Now, an example like this, I saw this one, this is a good one. Methylhydrazine, a liquid and rocket fuel. When 4 grams of it is combusted in a bomb calorimeter, the temperature of the calorimeter increases from 25 to 39.5. In a separate experiment, the heat capacity was measured to be 7.794 kilojoules per degree Celsius. Calculate the heat of combustion of a mole of methylhydrazine. Okay, so first thing we need to do, because the ultimate way to get heat of combustion, and heat of combustion really is delta H, right? What 2 things do we need in order to calculate that? It's going to be what over what? What 2 values do we need to find delta H? Q over MOL, moles, yeah, right. Q over moles. We need heat over moles to be able to figure that out. And this is heat of combustion, so it's really a delta H of combustion. Heat of solution would be delta H solution. Heat of neutralization, delta H neutralization. Okay, you get the idea? Okay. So we need Q first. How do we find Q? We can use our bomb calorimetry equation because they gave us the capacity. Right? C-cal, delta H. Alright, so this is negative 7.7 or whatever kilojoules per degree Celsius times the change in temperature, 39. That gives us Q. And what do we get for Q here? So this is degrees Celsius 2. You'll notice these cancel. What do we already get left over with? We get kilojoules. So I'm getting negative 113.0 kilojoules. That's our Q. All right, calculated Q, negative 113 kilojoules. That heated up the water. We know it's exothermic. Okay, good. So Q's all set for us in kilojoules. The sign's already been corrected because the heat capacity of the calorimeter is already factoring the sign change in for us, so we don't have to do that. The only thing left to do then is to find the moles, okay? We have to find the moles of the methylhydrazine and how much was put into the bomb calorimeter to begin with. 4 grams, so that means that 4 grams were inputted, so we can find the moles, okay? So change it to moles. I believe it's 46.09, but somebody can check that real quick for the molar mass. So how many moles of our methylhydrazine here? Okay, that's going to be what? 0.87.
67. It's 0.87. .08679.
679, okay, 0.08679 moles. Yes, we start out with 4 digits here, so we should keep 4 in our mole number. Then all we have to do over here is do the division, okay? And we end up with our delta H, which results in what number? Negative 1302, is that right?
Yes, negative 13.02.
Kilojoules per mole. Very good. Which makes sense that it's a higher number because we're talking about rocket fuel. Of course, that's going to have lots of energy released when it is burned. Okay? There we go. All right, this is the last one that I'm going to officially go over, and then we can talk about additional practice if you want to, or you can get working on some other stuff. But looking up here, you're going to be calculating the difference between almonds and cashews, their energy content. Now, calculate the heat in kilojoules gained by the water for each nut, the density of water. Notice they put the density here, right? So changing over, that means for our almonds, okay, we multiply this by the 1 gram per 1 milliliter. What are we going to get? We're going to get 2,000 grams. All right. Then all we have to do, because they provided us the specific heat of the water, the temperature change that happens from burning this nut. Okay, and it says burning, so you can pretty much know which way it's going. It's exothermic, burning, combustion, explosion. All right, so we do our Q equals MCAT here. And we have 2,000 times the specific heat. And the change in temperature is 40 minus 22.5 degrees Celsius. That gives us our Q. And this ends up being a large number. So once again, we're going to change it over to kilojoules like it says to do. So we calculate. This ends up being 150,480. Divide that by 1,000 joules. That's going to give you 150 kilojoules. So this is for the almonds. Now let's look at the cashews. And, you know, since we already showed how we converted the milliliters to liters over there, we can just go ahead and change this over to grams, okay? Since it's 1,000 milliliters to the grams there. And we just do the same thing. We use our Q equals MCAT. So 1,000 times the 4.18 times the temperature change. This one's a little bit higher, so 51 minus 22.5, like so. And we get our amount here. And this is 120,384 joules. So change that over. 1, 2, 3. So this is going to end up being 120 kilojoules. Don't forget your dot to make that significant. There you go. All right. So the calculate the heat gained by the water. So 150 kilojoules versus 120. And then which nut provides more energy per gram? So that's a simple calculation. What should we do to find that? Take our heat that was evolved and do what with it? Divide by the grams. Very good, because it says per gram, and guess what it gave us here? The grams, right? So that would be for the almonds. Over here for the cashews, 120 kilojoules, and the grams for that one is 5. And we can see which one is the better energy source, right? 150 divided by 6, this one's 25. 25 kilojoules per gram for the almonds. And this one is 24.0 kilojoules per gram. There you go, kilojoules per gram. So if you're looking for more energy per gram of nuts, you probably want to eat almonds instead of cashews. Although I'm sure both are pretty tasty. Yes, so almonds provide more energy per gram. This has all the detailed calculations here if you need to go back and look at it. Okay, now, a couple of things. There are some additional practice in here. You can do them. The last two have multiple steps, okay? Practice problem 3 and practice problem 4 go through more extensive, which would be probably more equivalent to what you would see in a longer FRQ, where it connects different concepts together, I believe. Additional practice number 4 has the gas laws in it too, like the ideal gas law at the end. So that's kind of something that connects in. And then the other one connects, like, you have to condense the steam into the water, and then the two waters, once it has condensed, now they have to reach thermal equilibrium, so that one occurs in like 3 steps. So you might want to check out 3 and 4. I mean, the other two are fine as well. The first one has the Maxwell-Boltzmann distribution graph here with the 2 different temperatures. Just remember when you're reading this graph here, this is velocity of the particles. So here is T1 neon. Okay, so this is mole of neon. Here's T2 of neon. Obviously, it tells you that temperature 2 is bigger than temperature 1, but you could also see that on the graph, because the ones that the particles are moving faster, that means they have more kinetic energy. That means their temperature must be higher. So keep that in mind as you're reading the graph. That's how you would do that. Okay? So I'm going to end that here, but the rest of the PowerPoint also, especially for 3 and 4, has really detailed solutions on how to work those problems if you want to check them out.